Okay, we're in Chapter 11, Section 1 of Barnett. This section deals with the constant E and continuous compound interest, which we've already seen the introduction of. So not a whole lot of new material there, but it's a nice reflection of what we've already done. So let's review a little bit. So by definition, if you remember, the number E is the irrational number, defined here. It goes on forever without any repeating patterns. And obviously on your various calculators, you should look for the key labeled E. That's how you're going to find it on your calculator. E, however, also happens to be defined in terms of a limit. And it's one of these two limits. Is the limit as n goes to infinity of 1 plus 1 over n to the power of n, or the limit as s approaches 0 of 1 plus s to the power of 1 over s. S here has taken on the role of 1 over n. That's the substitution we've made. And, well, if n goes to infinity, then obviously s goes to 0, and 1 over n gets replaced with s, and n gets replaced with 1 over s. We're going to look into that into greater detail in just a second. So, in fact, just to remind you, the formula for compound interest, P was the principal, R is the rate, T is the time in years, N is the number of compounding periods per year, and A was the amount realized at the end of the time period. In other words, the future value, what you get out of your investment in the future. So far, we've encountered formulas for simple interest and for compound interest, and today we're going to talk a little bit about continuous compounding, which we have briefly seen in the past, but we haven't done in greater detail. So what is really continuous compounding? Well, continuous compounding is, if I go back, if I take the formula for compound interest, and I look at n, the number of compounding periods per year, right? The number of compoundings per year, as it's called. If I make this n get larger and larger, if I make it become bigger, make it go towards infinity perhaps, right? Take n to go to infinity, then I'm saying that we're compounding interest infinitely many times. In other words, we're constantly compounding this interest all the time. Every instant, we're compounding interest. That's what it means to continuously compound. You're compounding interest every single instant that you could think of. So essentially, the formula that we have here for continuous compounding is going to be given birth to using the formula for compound interest and taking some limits. And here's how that's done. To derive this formula for compound interest, we start with our formula for compound interest, okay? And we take the limit as m goes to infinity of our formula, P times 1 plus R over M to the power of MT. So what we're saying is make the number of compounding periods go towards infinity. You're compounding every single instant as much as you can. Well, take the constant out, right? That's just one of the rules we learned for limits, that if you have the limit of a constant multiple times a function, you can get rid of that constant. You have P times the limit as m goes to infinity of 1 plus R over M. And what we're going to do here is we're going to insert an R over R in the exponent. So instead of having m times t, the power now becomes m over r times r over t. So I hope you notice this doesn't change anything because the r's could cancel out. So you're really back to m times t. Why do we do this? It might not be intuitive, but you'll see in a second what's the point of that. So on the next line, what we're going to do is introduce another substitution. We're going to let s equal r over m. Okay, if we let s equal r over m, then if m goes to infinity, then we have a quotient here whose denominator becomes infinitely big. So r over m should go towards 0. So s goes towards 0. So we can rewrite this limit in terms of s. So the limit as s approaches 0 of 1 plus, instead of r over m, now we have s. And over here, we have m over r. Well, that's going to become the same as 1 over s. Right? If s is r over m, then m over r is just 1 over s, right? It's the inverse of that. So that's how you could think about it. Okay, so using our limit properties, this is the same as the limit as s approaches 0 of 1 plus s to the power of 1s, the whole thing to the power of rt, and that gives us the value e. This here is the number e. So we're going to have p times e to the power of rt. So that's how this formula for compound interest is derived. So you should take a look at the textbook for more details. They give a pretty detailed example about that as well. We're going to take a look at another example. We're going to compare now the different types of interest that we have so far and sort of see what happens. So we have this generous grandma here, and she's going to put $1,000 in a bank just for you at 5% interest. And we're going to calculate the amount that's in the bank after 20 years. Well, using the formula for simple interest, all we have is that the future amount is P times 1 plus R times T. Right? The rate is 5%, which is 0.05. T is 20 for 20 years. After 20 years, we're going to have $2,000 in the bank. If we were to compound annually, right, then all that's changed here is this is still A equals P times 1 plus, how do we get the 0.05? Well, remember, this is the rate divided by the number of compounding periods. So in this case, that would be one compounding period because it's annually. Okay, and then it's to the power of NT. Once again, since N is 1 and T is 20, we get 20. And notice when the calculation is done, we get $2,653.30. So when the conditions are held the same, when the principal, the interest rate, and the time are kept the same, when those variables are the same, compounding annually turns out to be better than using simple interest if you compare those two amounts. Well, if we compound daily, we should expect that we get even more money. And in fact, we do. Because look what happens in this calculation. A equals P. Once again, we have 1 plus R over N, right? That's what this ratio here is. To the power of NT. Let me raise this because there's not enough room here. I don't want you guys to not see this. But we have P times 1 plus R over T. T is now 360 because that's how many days in a year there are, right? Raised to the power of 360 times 20. So, with that in mind, what do we get? We get $2,718.09. So that's an even better estimation than that's a better even better amount, than with compounding annually, just as we expected. Well, it turns out compounding continuously, right? Continuously increasing the number of compoundings or the number of compound periods. That's going to give us an even better amount because we're constantly compounding. We're continuously compounding. So what happens then is we use A equals P times E to the RT, and that's how we get $2,718.28. So by very little bit, but still better than compounding daily. So compounding continuously, if all variables P, R, and T are kept the same, is the best case scenario. Remember that. Okay, if some of these variables change, however, that's not the case. So something to keep in mind. Here's another example with an IRA. So after graduating from Barnett College, Sam Spartan landed a great job with Sprinketsbury Manufacturing, Inc. His first year, he bought a $3,000 Roth IRA and invested it in a stock-sensitive mutual fund that grows at 12% a year, compounded continuously. He plans to retire in 35 years. What will be its value at the end of the time period? All you have to do is use your formula here, A equals P times E to the RT to figure out the answer, right? And we know that P is going to be 3,000. That's how much was invested. And E to the power of 0.12 is our interest rate, right? The 12%. T is 35 because we have 35 years here. So that's the formula that we need to evaluate in part A. In part B, it says the second year he repeated the purchase, so another $3,000, since it was an identical Roth IRA. What will be its value in 34 years? So once again, we have to use the same formula here, where P is 3,000 again, but what's different here is we have 34 for T instead of 35. That's because there's 34 years left, right? I mean, it says what will be its value in 34 years. He did that on the second year. So that's why the calculation will change. And using a calculator, you could verify these values here in the answer. You should get about $200,000 in part A and $177,436 in part B. Okay, so one last example in this section, computing gross time. How long will it take an investment of $5,000 to grow to $8,000 if it is invested at 5% compounded continuously? Well, compounded continuously in the problem tells me to use the formula A equals P times E to the RT. The investment is $5,000 initially. That's my P, $5,000. I needed to grow to $8,000, which means that my future value is A equals to 8,000. Finally, I know that the interest is 5%, so my R is 0.05. Remember, it's in percent always expressed as a decimal. And what is it we're looking for here? Well, we're looking for t. That's what we don't know, how to find how long it will take for that to happen. The very first step here will be to divide both sides by 5,000. That will give us 8 over 5, or 1.6 on one of the two sides. So here's the calculation done for us. Divide both sides by 5,000, and we switch the two sides here to get 1.6 equals e to the power of 0.05 t. Then, to find t, we take the ln of both sides. And when we take the ln of both sides, on the right-hand side we get ln of 1.6. On the left-hand side we get ln of e to the 0.05 t. But you guys remember from the previous chapter that ln of e to any power, the ln and the will cancel out, and the 0.05 t, the power, is going to be what remains. So we get 0.05 t equals ln of 1.6. Divide both sides by 0.05 to isolate t, and that's how we get t is about 9.4 years. So that's how long it will take for the investment to go from $5,000 to $8,000.